Okay, so something new. Integration by parts. So if we write down the product rule for differentiation, we might get something like this. So we get, if you're differentiating u times v, which will be equal to, now something in this is not going to necessarily make sense, but we won't worry too much. I don't know, maybe we'll be okay. Maybe we'll be okay. Alright, well, look, I'll just write something down. If you want to make this more precise, it is possible. So the first thing by the derivative of the second thing, plus the second thing by the derivative of the first thing. And now what we're going to do is, we are going to differentiate both sides, anti-differentiate both sides with respect to x. Okay, so this is kind of nonsense, but let's go. So if you anti-differentiate the left-hand side, you're going to get u times v. Now, anti-differentiating this with respect to x, I'm just going to write it as it is. So you get u dv dx with respect to x, and because anti-differentiation is linear, we can anti-differentiate this and then anti-differentiate this. We can do kind of nonsense stuff, which is dx over dx is 1, and you get antiderivative u dv plus antiderivative v du. And then you can take away the antiderivative of v du from both sides, and you get this little formula here, which is what we're going to use. Alternatively, you can kind of almost define this du to be du dx by dx. And again, it's all kind of, all what I'm saying is nonsense because du dx is not a fraction, but you can show that it all works. Okay, so this is the product rule backwards. Now it's not exactly the product rule because it's not like you've two things multiplied together, but in practice it's not far off. So this is called the integration by parts formula, and this is a new technique for you, and one that you haven't seen before, but it's our fourth technique. So the first thing is, can you do it directly? Then is there manipulation? Then try a W substitution, and if that doesn't work, you try parts. Okay. This involves a double substitution. You're confronted with an antiderivative. You pick the u, everything else is the dv, and then you kind of go through these things and you calculate them and you put the formula back together. It can help if to pick the u, you use Liate. We will explain why Liate works. So it's given here, right? So you pick u to be the first thing on this list, and therefore dv will be underneath. So whatever you do, it'll be like u, and then underneath you get dv, because dv is everything else. Now look at the formula. U, which you'll have picked, v. How you get from, and we'll do this over here in a moment, how do you get from dv to v? You have to anti-differentiate / integrate dv. And the way this is set up is the things on the bottom here are easy to integrate and the things on top are hard to integrate. And in anti-differentiation is more difficult. So in Liate, you make sure that you pick something that, you pick the u in order that the dv is easier to integrate. I don't know if that's a great explanation, but that's what it is. Okay, so one thing here is like, how do you go from looking at this formula? Now u from du, u to du should be okay, because if you want to get some du's knocking around, you need to differentiate u, so that should be okay. But how about the dv to v? Question mark. Now there's various different ways that I can explain this. Okay, there's various different ways. Okay, so the first one is kind of a mathematical one as such. So look, consider the antiderivative of dv. Now that doesn't really make sense, because this means this is, what are we anti-differentiating? Well, if there's nothing there, presumably we're anti-differentiating 1. That makes sense. 1 by dv is dv. This can be make happen a bit. You can change this formula slightly, and this specific problem kind of disappears. But anyway, and then the question is, what is the antiderivative of 1 with respect to v? So what is the thing that you differentiate with respect to v and you end up with 1? Well, the answer would be v. So this is one explanation of it. If you want to get v, I'm going to say anti-differentiate dv, which is a little bit dodgy, but anyway, that's one way of doing it. There's another way which comes from an understanding of what integration actually is, and that understanding, which I haven't spoken about here so much, maybe I will in a later section, is that integration is adding up loads of little things, and what this dv represents is a little change in v. So this is adding up all the little changes in v, or the little bits of v will give you v. So whatever way you look at it, now this, if you look at it, it's, oh, you're going to u to dv. That's not actually what I mean. That's not going to happen. I'm just saying that in the ate, you pick the u first, and so the dv is underneath, and what that means is dv is something that's easier to anti-differentiate. Okay, probably at this stage we need to look at some examples. Basically this formula, which is in the tables and on the exam paper, is what we're talking about. Right, so probably one thing we should say here is that you won't be prompted necessarily to use integration by parts. So in theory you should actually go through the strategy. So the first thing in the strategy is, can I do it directly? Because they're multiplied together, you cannot do it directly. It doesn't work, because you can't. You've got, like, if I spread this out a little bit, I have 5t e to the minus 3t. I can't anti-differentiate term by term because it's not a sum, they're multiplied together. So direct is out of the question. Manipulation, there's no manipulation here. I mean, you could write 1 over e to the 3t, but that's making things worse. So then it suggests you should try a W substitution. Now the W substitution isn't going to work because you haven't really got function multiple of derivative. Like, this is minus 3t has derivative minus 3, and this is 5t. It's not a multiple of minus 3. It doesn't work. If you try and do it, the only obvious thing to try is minus 3t because it's inside the exponential function, and you end up with this yoke, 5/9, and this is not in the tables. You try and do manipulation here, there's nothing you can do. There's no substitution here. You're never going to do, let's say, w equal x, because all you're going to do is change all the x's to w's. It's not going to work. So those three things have not worked. You have to do integration by parts. So we'll write probably this integral on top of the next page, and also the formula. Okay. So writing the antiderivative up the top of the page, we're looking at 5t e to the minus 3t dt. And the formula, we're going to try integration by parts. The formula says antiderivative of u dv is equal to uv minus antiderivative v du. Okay. So our job is, so this would be playing the role of, this is the u dv, and we're going to write it hopefully as a sum of simpler things. That would be the hope. We have to do the u first, and I recommend using Liate. So the L stands for logs. There's no logs here. The I stands for inverse trig. There's no inverse trig here. The A stands for algebraic. Now algebraic is like sums of powers of x, etc., which I probably should have put back here. We'll just go back. So logs, you understand. Inverse trig is like inverse sine, inverse tan. Algebraic here means like x, x squared, etc. Powers of x. In this particular question, we're not working with x, we're working with t, so 5t is the thing. Now you might be tempted to say, oh, minus 3t is algebraic as well, but look at the u, it's multiplying, it couldn't be minus 3t. So the u is going to have to be 5t. So you pick the u, everything else is dv. So here's u, everything else is dv. So I have, and you can see now why when I was talking about substitution, I didn't use u anymore, I used w. So yeah. So we get dv is equal to everything that's left, e to the minus 3t dt. Okay, now think about your formula. So we have in the original call this I. So I, which remember is this thing, is equal to uv. So u I picked as 5t, and now I need to get from dv to v. Okay, so how do you get from dv to v? Well, we said this on the previous page. However way you want to think about it, if you want to get v, you need to integrate / anti-differentiate dv. So v is the integral or antiderivative e to the minus 3t dt. You've got a little antiderivative. You look in the tables, and what you see is, maybe let's grab a little scrap of paper. If you look in the tables, what you will see is the antiderivative of e to the ax is 1 over a e to the ax. So the antiderivative of e to the minus 3t is in the tables. So the a will be minus 3, and obviously rather than x we have t. So the v is 1 over a, in this case minus 3, e to the ax minus 3, and rather than x it's t. Okay, so we've got u, we've got v, which is 1 over minus 3 e to the minus 3t, minus v, which is here, and now what we have to do is find du. So we said that to get du you need a relation. Well, how do you get a du? You need to differentiate u. So du dt, not du dx here, because this is a function of t. The derivative of 5t is 5, and you're looking for du, multiply both sides by dt. Now again, multiplying by dt is nonsense, but you can show it always works. So this is 5 dt. So just showing that we have used this formula, we've identified the u and everything else is the dv, and we use this formula up here, and this is u v minus antiderivative v du. So we have used this formula. Okay, now let's tidy this up a little bit. Space isn't magnificent, but anyway. So here we've got 5 by t by, now plus over minus is minus, so this is minus a third by this. What I recommend is we do, this will be negative, this will be positive, so plus by minus is minus. 5 by a third is 5 thirds. We've t times e to the minus 3t. Okay, we'll do a similar story here. We've got 5 by minus a third, that's minus 5 thirds, but it's multiplied by minus, well, hang on. So I've got minus 5 thirds, it's a constant so I can fix it. That means basically take it out in front of the antiderivative, and you got minus by minus 5 thirds, minus by minus plus, plus 5 thirds, antiderivative, e to the minus 3t dt. Okay, good. And now this thing is in the tables. So now what I'm probably going to go for is I'm going to just anti-differentiate this. I'm not going to worry too much about the manipulation multiplying out at the end, but I will put in the c. So this is minus 5 thirds t times e to the minus 3t. I'm going to fix that 5 thirds, and then the antiderivative of e to the minus 3t is 1 over minus 3 e to the minus 3t. You could multiply these two things together, I'm not too bothered by that. And of course it's an antiderivative, no integrals, so it's plus c. If you want to check your answer with these, because it's running the product rule backwards, to check your answer you'll usually need the product rule. So here, to differentiate this you need the product rule, but you can differentiate this, see do you get the original 5t e to the minus 3t. Right, so that's an example. Let's drive on. Okay, x log x. Let's go through our strategy. It's now x on its own is in the tables, log of x isn't, which we might explain why soon. But it doesn't matter, they're multiplied together, so I can't anti-differentiate term by term anyway. So the next thing is manipulation. There's literally nothing you can do to rewrite this. a substitution, there's no substitution because all you can do is w equal x and it doesn't go anywhere. You're never going to do w equal x. I'll just change the x's to w's. And doing w equal log of x, it's an idea, but it actually, it doesn't really change things up that much. So we need to do integration by parts. So what we're going to do is we're going to write down our formula. Okay, and we need to pick u by Liate, and then everything else is dv. So we go through our Liate. So L is logs. Are there logs? Yes. So what that means is log of x is our u, and everything else that's x by dx is our dv. Okay, now we'll come over on the side here to figure out what's going down. We're calling this thing I. Go over to the left here. So under uv, this is the formula. So u we've chosen to be log of x times v. Now we've said it already. If you we know what dv is. It's x times dx. And if you want to get v, you integrate dv. So this is v, which is integrate both sides, is integral of x dx. Now to anti-differentiate x, you have to recognize that x is x to the power of 1. And so to anti-differentiate x, in other words, to anti-differentiate x to the power of 1, it's x squared over 2. Okay, you don't need the plus c here, by the way. Long story, but just take my word for it, I would say. Yeah, so there's no need for plus c, just a plus c at the end. Long story, we won't worry about it. So this is times x squared over 2 minus antiderivative of v, which is x squared over 2 times du. Now how do you get du? Well, to get du, you differentiate u. We've said that u is equal to log of x. So if you want to get du, you differentiate both sides. So you get du dx, and the derivative log of x going to your tables is 1 over x. We're looking for du here, so multiply both sides by dx. You get du is equal to 1 over x times dx. So we end up here with du is 1 over x dx. Right, so just being clear, we've done u v minus antiderivative v du. Good. Now I'm going to write the log x by x squared over 2 the other way around, because there's a possibility that someone might think that the x is multiplied by x squared over 2, but it's actually the log of x. So doing that will remove that possibility. Now what about this next yoke, this thing? Okay, look at this. It's not in the tables because it's multiplied together. You can't anti-differentiate term by term when they're multiplied together. So tables is out. Next option is manipulation, and luckily the manipulations are here. First of all, divided by 2 is the same as multiplying by a half, and anti-differentiation is linear, so you can fix the constant a half. And then there's a kind of a handy one, x squared divided by x. Well, that's just equal to x. So that's a manipulation here. So like the one thing we probably said is that, oh, this is a big antiderivative. It involves, okay, there's different things. It's like a ping, ping, ping. It's like you take 2 steps forward, 1 step back, and that's going 1 step forward. You're anti-differentiating this, but this thing needs to be integrated as well. And this could, in theory, need integration by parts or anything. Here, it just needed a little manipulation, and now we can go x squared over 2 log x minus fix the half. And now what is the antiderivative of x? Well, we've seen it over here. It's x to the 1, so its antiderivative is x squared over 2. We could, if we wanted, simplify this. This will be x squared over 4, but I'm quite happy how it is. Plus c. You can check your answer by differentiating this. See, do you get x log x? It'll need the product rule, as we said. You don't need the plus c earlier on, but you need it at the end when the final, I would say, antiderivative is calculated. I think what happens is if you include the c here, what happens is you get a u by c, and here you end up with a minus c by u, so there's no point putting it in till the end. I think that's the answer to the question. Okay, we'll drive on. We'll do another example. Whoa. Okay, so there's a few pages left out here. So the next example, which I don't go through, and it won't really be examinable, it's just kind of emphasizing that this thing here can need different rules of you have to take the strategy to this. I think what happens in the next example on the next few pages is that when you get to here, this thing, it can't be done directly. No manipulation will do anything. Substitution doesn't work, so actually this itself needs integration by parts. So it's a double integration by parts, and that can happen in general. Okay. So where are we? So yeah, we'll do this final example here, and we'll leave the next example to a later video. So here we have an integral. What am I going to say? I would say that if you're doing a W substitution integral, that what you should do, I have to go back. Say, for example, this is only an antiderivative, so there's no limits. But if it was an integral, what I would do is, when I go to here, I would forget about the limits. I'd forget about the limits. Only when you go back to x would I put the limits back in. So basically what I'm saying is that if it's the antiderivative is anyway complicated, forget about the limits for the moment, and then just do the integration at the very end. You'll see what I mean with this next example. So similar story here. Now here you think this is in the tables, but they keep it out of the table, so we have a good example here. Okay, so it's not in the tables. You think it is, it's not. There's no manipulation. There's no way you can rewrite log of x here. Substitution, the only option is w is equal to x, which doesn't change anything. And I think if you do w equal to log of x, you probably end up with e to the w. That actually is a possible way of doing it, which is interesting, but I won't. Oh, I think I tried that before. It doesn't really work. So we need to do an integration by parts. So let's write the formula for ourselves again. Okay. So, right. So, according to Liate, we pick U to be the first thing on the Liate list. And L stands for logs, there's a log. So this is going to be the U. And then everything else is dv. Okay, that's written there. U is log of x, and dv, well, it's simply dx. Okay. Now, let's go at the formula. So what I'm going to do is we're going to forget about the limits for a second, and we're just going to look at the antiderivative of log of x. So let's do u, which is log of x, by v. Now, we'll do, so we said dv is equal to dx. Now, if dv is dx, it doesn't actually mean v is equal to x, but for the purposes here, it will. So we're going to integrate both of these. So v is equal to the integral of dx. And for the same reason that the integral of dv is v, the integral of dx is just x. So I remember you can pause this video. You can email me questions if anything isn't clear. So that's uv minus, using this formula, v, which is x, times du. Now we need to get du. So we've chosen u to be log of x, so to get to u we differentiate that. Derivative of log of x in the tables is 1 over x, and now we multiply both sides by dx, and you end up with du is equal to 1 over x times dx. Space is not great here, but we'll be okay. Okay, so log of x by x could possibly be confused for log of x squared when it's not. So I'm going to write that as x times log of x minus. Space is not ideal here, but there we've got a bit of space on here. Okay, this thing cannot be done term by term because they're multiplied together. So there's no point going to the tables. You have to do manipulation. And here we've got x by 1 over x. In other words, x divided by x. This is just 1. And what is the antiderivative of 1? What do you differentiate to end up with 1 with respect to x? Well, it's just x. So you get x log x minus x. Now, because we're doing an integral, there's no need to put in the plus c. Off we go. The integral. Now, what I was saying previously was that if you've got an integral where the antidifferentiation is complicated, just do the antidifferentiation and then come back, and then you can do the integral in one line. Because to calculate an integral, you need to do an antiderivative. The antiderivative of log of x is x log x minus x. And then we say substitute top limit minus substitute bottom limit. So you end up with e log e minus e. That's substitute top limit minus 1 log 1 minus 1. So e log e minus e, the top limit minus bottom limit 1 log 1 minus 1. You can go into this in the calculator if you want. Maybe just show you where the e button is. If you want to do e, probably the easiest thing would possibly, depending on the calculator, it could be e to the 1. That gives you e, approximately 2.718. I won't use the calculator. I'll try and do this in my head. Log of e is equal to 1. So this is e by 1, which is e. E minus e is 0. Log of 1 is 0, so this is 0. So you just end up with minus minus 1, which is plus 1. Okay. Now just to finish off this video, what we might say is, okay, we said at a previous lecture that integration is just finding an area. So 1 is the area of this. Now what I'm saying is this shape looks a little bit like a triangle, so we can get an underestimate of it using a triangle. What I'm saying is the area of this triangle should be kind of close to 1. So I'm going to say, and I'm going to be reasonably confident looking at this graph, that the integral from 1 to e log of x, which is equal to the area, is going to be bigger than, because of this extra bit, it's not equal, it's bigger than the area of this triangle. And the area of the triangle is half the base. The base of this is e, and the height is 1, so it's half e, and I'll do that on the calculator. I get something going wrong. Half the base. Oh no, it's not e, it's e minus 1. And let's see what this comes out to approximately. So 1/2 oh dear, and I'm running out of time, so this is not ideal. E to the 1 minus 1 divided by 2.859. So that means that little area in there is about 0.14. Okay.